Guys, good morning. We start. I think very less number of people joined. 2, 3, 4, 5. 5 are there. Shall we wait for 2 more minutes? Let your friends join, and then we'll start. Okay, we'll start. So, if you can remember, that we were doing surface chemistry, isn't it? So, I told you in surface chemistry there will be 3 parts. So, one relating to adsorption, another relating to catalysis or catalyst, and then the last thing talks about colloids. Correct? So, we finished adsorption. Correct? So, we'll move on to what do you want to go? You want to study colloids or you want to study catalyst? You tell me. Hello, guys. So already there. Ajay, Akshay, Akshanya, Shruti, Srinivedita, Tarun. Guys, are you able to hear me?
Yes, sir.
Okay. So you want to start with catalysis or you want to start with colloids? What do you want to study? You tell me. So you don't want to make your choice. Isn't it? You don't want democracy. Fine. Okay. I'll start myself. So we'll start with catalysis. Okay. Then we'll move on to colloids. So we are going to study about catalysts today. Right. Okay. Fine. So we already know what catalysts are going to do, right? So catalysts are the one which will alter the rate of the reaction, right? But again, it's a very common misconception that catalysts are only going to increase the rate of the reaction. Need not be always, right? So there are going to be cases where you will see the catalyst in some form will be able to reduce or say decrease the rate of the reaction also, right? So in general, how can I define catalyst? Catalysts are the chemical species, right, which is going to alter the rate of the reaction without much involving in the reaction, right? Without much taking part. I will not say strictly it will not take part in the reaction because, especially in organic chemistry, if you have seen the mechanisms, you would have seen that catalysts do take part in the reaction. But eventually, when the reaction is going to get, say, it is going on, at some point of time, the catalyst would have gone out of the reaction. So eventually, ideally speaking, right, catalysts actually don't take part in the reaction, right? That's how it is. But again, we'll not be able to say, strictly speak that it is not going to take part in the reaction, right? But what I can say is that they are definitely going to alter the rate of the reaction, either decrease or increase. That is going to happen, right? Okay. So based on that itself, whether they are going to increase or decrease the rate of the reaction, right? So I will be able to divide them into 2 types, right? Say first one are what are called as activators, and the other one are what are called as inhibitors, right? So I think that from the name itself, you'll understand what I'm trying to tell you, right? So activators are the one which are going to increase the rate of the reaction, right? And inhibitors are the one which are going to decrease the rate of the reaction, right? So This can also be called as activators, can also be called as promoters, right? And inhibitors can also be called as poisons. These are different terminologies given to activators and inhibitors. So activators are called as promoters, inhibitors are called as poisons, right? Fine. Let me take some examples. I think you would have seen humorous examples for the case of promoters or say activators. That means they're going to increase the rate of the reaction. So many are there, like so many. Say the simplest of example would be Haber's process, where I form ammonia, N2 plus 3H2 giving N2NH3. So here I know I use Fe as the catalyst here, isn't it? So many reactions, like I'm just giving you one, right? And then say if I go to inhibitors, right? So inhibitors are going to decrease the rate of the reaction, right? So by which example I can take, you have already studied it, right? So this is the example. If I have CH2 double bond CH2, if I put palladium poisoned with BaSO4, obviously H2 should be there, and you would have found, you find that I'm going to form ethane, right? So now what you see here is this palladium poisoned with BaSO4, right? Right. So palladium is actually palladium with BaSO4 is actually going to act as an inhibitor here. It is going to act as a inhibitor, okay? Because this rate of reaction is very violent, right? So I don't want that to be. I don't want it to be that violent. So I put a inhibitor, that is palladium poison with BaSO4, that is going to decrease the rate of the reaction here, right? So this is a very good example for inhibitors or poisons. Okay, right? Good. So yeah, these are the basic terminologies you have to know and the examples, right? So moving on. There are mechanisms suggested. Basically, I know catalysts are going to I know that catalysts are actually going to alter the rate of the reaction, but how they're able to do it is the question, right? How they're able to do it is the question. That means I have to study about the mechanism of how that happens, right? Like obviously it is going to be reaction specific, right? Depending on like obviously you have so many types of catalysts in organic chemistry. So the way they will like each and every catalyst will be able to change or alter the rate of the reaction depends on the reaction. I'll not be able to tell that constantly this is what is going to happen and all that. But still, for some good number of reactions, right, I'll be able to tell a general mechanism, right? I'll be able to tell a general mechanism, and that mechanism is actually going to be based on adsorption, which we have studied earlier, right? Adsorption, a few more classes before we studied, right? So based on adsorption, right, there is one mechanism by which I'll be able to explain what to say, how catalysts are able to increase or decrease the rate of the reaction, right? So we'll see what is the mechanism. So we are going for mechanism of catalysis with respect to adsorption, obviously. Right? With respect to, with the help of adsorption, we are going to explain how catalysis is happening. Catalysis means the phenomenon of using catalyst to alter the rate of the reaction. That's it. Catalysis is the phenomena. Catalyst is the chemical species. Okay. Again, I repeat. Catalysis, if I say, it is the phenomena of using catalyst to alter the rate of the reaction. Catalysts are the one who does it. Right? Catalyst causes catalysis. Something like that. Right? Okay. So we are saying about the mechanism, right? So I wanted to write down because this particular mechanism, whatever writing, have been asked in 3 marks or even 2 marks in your board exams. So I would say it is a little important, right? Okay. So we'll see what are like it's just a step-by-step process. It's very easy to understand. Okay. So we are going to see, especially if the reactants are gases, right? We are going to see, especially this will work wonderfully if the reactants are in gaseous phase. Okay, the reactants are in gaseous phase, right? Okay, so we'll see what is going to happen. Right. So I'll just tell you the general idea, and then we'll take it down what are all the points we need to have, right? Okay. So like here, what is going to happen is the catalysts are going to provide you the surface, right? The catalysts are going to provide you the surface for the reaction to happen. Okay. We already saw this example when I studied about adsorption. If you can remember, I told the same example: CH2 double bond CH2 adding with H2 to form ethane, right? So there you saw nickel acting as catalyst, nickel or palladium or platinum, all these B block elements acting as catalysts, right? So I told you how at that time it works. So if you can remember that, right? So I have the, say for example, this is the catalyst surface, right? So I'm going to have the catalyst surface, right? So catalysts are actually, see, I told you, right? Like it is the mechanism of catalysis is actually going to be reaction specific, right? Depending on the reaction, how catalysts are able to do that will be so different. And I would say still research are going on, right? So there are cases where the catalyst is able to increase the rate of the reaction multifold times, but scientists don't know how exactly they are doing it. Like it's a very good area of research, right? How, where, and how all these mechanisms and all these. But still, here it's a very general mechanism for your basic understanding, right? So, like if at all you find any other this thing, it's well and good. It's correct, right? Okay. So here, the what does catalyst do is that the catalysts are going to provide you the surface for the chemical reaction to happen, right? So if this catalyst was not there, right? If this catalyst was not there, and especially if I have gases, right? So I know gases, they are like the interparticle space between the gaseous particles are very high, isn't it? The interparticle space, I know, between any two particles in matter, either solid, liquid, or gas for that matter, will have some interparticle space. And obviously, solids have the minimum space, and gases have the maximum space, isn't it? So the thing is, if I want to make a reaction between two solids occur, right? If I have two solids, say for example, calcium reacting with, or say calcium chloride reacting with sodium, right? So both these are solids there. Calcium chloride is a solid salt, sodium is a solid, right? So there, I would say, see, if you want the reaction to happen, the reactants must be in contact, right? So obviously, you are studied about collision theory, right? What does collision theory says? Collision theory says that the reactant molecules has to undergo collisions, right? And obviously, these collisions, if they are successful, and you know what are all the conditions required for the collision to be successful. So if it is successful, I'm going to end up with products, right? So you can easily understand that this collision has to happen. For this collision to happen, the reactant molecules, say two reactants or three reactants or whatever it is, they must be in strong contact, right? So more and more they are in contact, more and more collisions will happen, more and more effective collisions will happen, and so more and more product formation, right? Now, if this same thing is considered with gases, right? So having this contact, bringing them together is actually a task, right? It's actually a task in itself, right? So then I have to check whether they will react or not, and if they don't react, again, some other things, the temperature has to be increased or pressure has to be decreased. Something, again, reaction specific. It depends, right? So if I'm going to use this catalyst, that for that problem of bringing them closer, or say bringing them into contact, is actually the job done by your catalyst here, right? So because gases are going to have very high kinetic energies, they'll be moving here and there, like so. Bringing them closer, right, is the job done by your catalyst here, right? Fine. So the first point, right? So we understood that the catalysts are going to provide you the surface for the reaction to happen, right? So just by providing the surface, like so, what I can just put, like if I have a beaker, so this is the beaker, right? So this is closed beaker, and I bring it slowly towards the catalyst, and I open it. Is that how it happens? No, like that's not exactly how it happens. So the thing is, people, here adsorption is going to be there, right? Because if at all it is going to provide you the surface, like obviously the reactant molecules has to get, like say it has to stay in the catalyst surface for some little amount of time, isn't it? Only then, or like as long as they stay, right? Obviously, then only they will be in proper contact and the proper reaction will happen, right? So definitely I have to hold these reactant molecules together on some surface. So that holding force is what is my adsorption here, right? The holding force is what is my adsorption, right? Okay, so the first point what you have to understand in catalysis, I mean the mechanism of catalysis with respect to adsorption is that first thing, I'm going to have diffusion of the reactants, diffusion of reactants to the catalyst surface. This is the first point you have to remember, right? I know gases can diffuse. Again, see, there are two types. The diffusion term is used in two places. One, when you talk about the movement of solute and solvent and all that, right? And another way is when I say gases can diffuse. Diffuse means to move, right? Or I don't know whether you have studied, remember your ninth class, right? There I would have studied about states of matter, or not states of matter. I think matter and our surroundings. That was a chapter there. So you were introduced to solids, liquids, and gases, right? So there you would have studied this, the process of diffusion. What do you mean by diffusion? Like how will I simply explain it? Say I have a beaker, or say I have a vessel in which there is a partition. Okay, I have a vessel in which there is a partition. Say this side I put N2 gas and this side I put O2 gas. Okay, so now they are not in contact. So now what I do is I remove the partition. What will happen? Will, like, even after removing, do you think they're going to stay in their own positions? Definitely not. They have high kinetic energies, so they will be mixing nicely. I don't know whether chemical reaction will happen or not, but definitely mixing will happen. Right? The nitrogen gas and the oxygen gas will start mixing. Again, if the temperatures and pressures and other things are suitable, maybe a chemical reaction might also happen. Right? So this process of intermixing of gases, right, is what is called as diffusion. Right? I mean, the nitrogen gas and the oxygen gas are going to mix together nicely because there is no partition there. So that mixing is what is called as diffusion. So basically, in crude words, the movement of gas is what is called as diffusion. Gases diffuse is what you have to understand, right? Okay. So first thing is you're going to have the diffusion of reactant molecules towards the catalyst surface. So they're going to come near the catalyst surface, right? Okay. So when they are near enough, when they are close enough, right? Now the adsorption kicks in, right? So second step is that I'm going to have adsorption of the reactant molecules onto the surface of the catalyst, right? Reactant molecules are going to get adsorbed onto the surface of the catalyst, right? So the gases will first come, right? Everything will come, and then you will have adsorption happening, right? The gases are getting adsorbed now, right? So there are so many two or three reactants there. All the gases are going to get adsorbed. Okay. Now third point, right? Now they're adsorbed. Now whatever I want, the very reason which I use catalyst we have come true. What is the reason? I want to make sure that these gas molecules are in contact, are in good contact. They undergo a good number of collisions, and so they gave me the result, the product, the end result. Isn't it? So what I was telling, so it happened now. So that means they are in contact. All the reactant molecules are in contact, right? So now what will happen? Chemical reaction will happen. So the third point after adsorption is my chemical reaction. So this is the step where the reaction happens, right? The first step is diffusion, that is the gas molecules come near the surface, and when they are close enough, they get adsorbed onto the surface of the catalyst, right? So now when they're adsorbed, they are very strongly held in the catalyst surface, so the gas molecules will be in proper contact. So then the chemical reaction happens, right? Okay, now the chemical reaction will be happening, and at the end of the day, the products are going to get formed, right? So after the products are formed, now again, it cannot stay in the catalyst surface, right? I have to get the product out, right? The products cannot be there in the catalyst surface anymore, right? So I have to get it out. So that process is what is called as your desorption. So it is exactly opposite of adsorption, right? So the reactant molecules are adsorbed, product molecules are desorbed. That is, the bond is broken. That is the interaction between the catalyst and the products are broken, right? So that's the fourth point, desorption. And obviously now, not only desorption is enough, you have to entirely take it out, right? So again, what is going to happen? Diffusion is going to happen. Now, diffusion in this case, you saw it's the diffusion of reactant towards the catalyst surface, right? Now, the last point is going to be diffusion of products away from the catalyst, right? It's the diffusion of products away from the catalyst. That's it. So this is a very, very simple mechanism, right? So you would have understood. First, the reactants come. So first thing is the catalysts are going to provide to the surface, right? So what is going to happen? The reactant molecules are going to come. They're going to diffuse, diffuse, diffuse. They're going to come and get adsorbed onto the surface of the catalyst, right? So when they get adsorbed, they are in proper contact. So the chemical reactions happen. So the products are formed and the products are desorbed. That is, the interaction between the catalyst and the products are broken. And after that, they'll slowly diffuse and go wherever I want it to go. Like I will take it in whatever the vessel or whatever the machine which I have to take, I'll be taking it. So that would be diffusion of products away from the catalyst. That is how, that is the mechanism proposed for catalyst with respect to adsorption. Okay, right? Cool. So the guys, the 5 points, if you just write these 5 points, not even diagrammatic explanation required, if you just write these 5 points, 2 or 3 marks, just like that. Okay, cool. So we studied about the types of catalysts. We studied about how catalyst, like how catalysis happens, what is the mechanism behind it, and now we'll move on. We'll move on to types of reactions itself. Like there are, like you know that there are going to be reactions where catalysts are used, right? So this catalytic reactions, I'll be able to classify them into 2 types. Okay, so we're talking about catalytic reactions. Right? We're talking about catalytic reactions, right? So, I mean, catalytic reactions means reactions where some catalysts are used. Very simple, right? So these catalytic reactions can be of 2 types. Okay, so they are homogeneous catalysis right? And another thing is obviously heterogeneous catalysis. Okay, so it's again very simple. Like what you have to understand is what is the phase of your catalyst and the reactant molecules. Okay, what do you mean? What is the phase of the reactant molecules and the catalyst, right? So I think you'll be able to guess what I'm trying to say. If the catalyst and the reactants, if the reactants and the catalysts are in same phase, right? If the catalyst and reactants are going to be in the same phase, now that particular reaction is what is called as homogeneous catalysis, right? If the reactant molecules and the catalyst which are going to use are in the same phase, say liquid, liquid, gas, gas, like that. If you have, why am I not telling solid, solid? I'll come to that. So anyway, so generally speaking, you will see that reactants and catalysts, if they are in same phase, it is going to be called as homogeneous catalysis, and exactly opposite them, right? So here you're going to have reactant molecules and the catalysts are going to be in different phases. Solid, 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 solid. Okay, solid, liquid, liquid, gas. All these things are going to be in heterogeneous catalysis, right? So here the reactants and the catalysts are in different phase, right? The reactants and the catalysts are in different phase. Okay, fine. So I told there is something wrong about solids here, right? There is something wrong about solids. Here's 1 second. I'll just close the window and come. I think there's a glare. Okay, so there is something special about, not special, something, there's an exception when it comes to solids, especially, right? So, guys, even if you see, write a note, right? Take a note, right? So the note says, so the note says, even if the catalyst and the reactants are in solid phase, even if the catalyst and the reactants are in solid phase, it is called heterogeneous catalysis. It is called heterogeneous catalysis. Okay, right? So why is it like this? It's very simple, right? See, uh, if it is a liquid or a gas, right? Say if at all the what to say, the reactant molecules and the catalyst are both of them are in gaseous phase, for example, right? So what will happen? Definitely they will be able to intermix. Like the catalyst and the reactant molecules will be actually mixing, and all these things will happen. Same thing can happen with liquids also, right? Same thing can happen with liquids also. They'll be able to mix nicely. But will I be able to have a homogeneous mixture with all solids? That's the question mark, isn't it? So that's why whenever we see, even if one of them, that is with the reactant molecule or with the catalyst, if it is a solid, I will just blindly put that it is going to be a heterogeneous catalysis, right? So even if you find that the solids and the catalyst and the reactant molecules are going to be in solid phase, even though the phase is same, but it is going to be called as heterogeneous catalysis, right? Or even if one of them is going to be a that is reactant molecule or the catalyst, even if one of them is going to be a solid, then blindly I will put it is going to be heterogeneous catalysis. Okay, so if at all you want examples, I'll be able to give you. So best example for homogeneous catalysis is esterification, right? So hope you remember what happens in esterification, or it is, anyways, either esterification or hydrolysis of ester. Either of it will be, because both are reversible reactions. So I say I take hydrolysis of esters, right? So I have R COOR dash, right? So now when I go for H plus bar H2O, you will see that I'm going to form RCOOH plus R dash OH, right? So you see that these two are the, this is the reactant here, and this is the gas. So obviously this is in liquid phase and or aqueous phase. This is also an aqueous phase, right? Both of them are in liquid phase basically, right? So this is a very good example for homogeneous catalysis, right? Both the reactant molecule and the catalyst they are going to be in same phase, and none of them are solids. That's what is more important, right? None of them are solids. The moment you see solids, say I don't care about the products, people, right? Products, that doesn't matter to me. It is only about reactants and the catalyst. Products, even if they say for example liquid, and there is a solid here, still it is going to be a homogeneous catalysis. So we don't generally take into account of products space, right? We generally compare only reactants and the catalyst space. Okay. So yeah, so that's an example for homogeneous catalysis, and there'll be a lot of other examples given in your book. Just go through it. Okay, a lot of examples will be given. So 2-3 examples for each of them will be good enough. Okay, fine. So now when I go for heterogeneous catalysis, right? So yeah.
So, sir, can you repeat the reason why solid and solid catalysis, like those are heterogeneous?
Very simple, right? So the thing is, solids, say I have NaCl with me, okay, and say I have sugar with me, okay. So both are solids, right? So now if I try to mix them nicely, right? If I just try to mix them, like you can call it as a homogeneous mixture, but it is actually not. I know what is a homogeneous mixture, isn't it? So homogeneous mixtures are going to have the concentration of both the components, the solute and the solvent or whatever it is, throughout that particular mixture, it should be constant, right? So that kind of thing will not be able to get if the reactant molecules or the the catalyst molecules are going to be in solid phase. But if it is in liquid phase, or say in gaseous phase, that mixing of catalyst and reactants together will happen. So they will form a homogeneous mixture. Homogeneous mixture of what and what? Homogeneous mixture will contain the solid, the reactants, and the catalyst. So they will form a homogeneous mixture. But this homogeneous mixture is not possible if I'm going to have solid phase. That's what I'm trying to tell you. Did you understand?
Yes, sir.
Okay. So done. So that's about homogeneous catalysis. So heterogeneous, again, umpty number of examples. The moment you see solid catalyst, it's done. So one example which we already know. What? Look at this. CH2 double bond CH2 plus H2. This is in gaseous phase. This is in gaseous phase. But here you see nickel is a solid. Again, this is an example for heterogeneous catalysis. Right? Again, Haber's process, ammonia, N2 plus H2 in the presence of iron forms ammonia. All the things are gases here, but again, this is a solid. Right? So these are the examples for heterogeneous catalysis. The phase of the reactants and the catalyst are going to be different. Okay, cool. So that's about the types of catalysis. Okay, so in heterogeneous catalysis, there is a one special thing which can happen. Right, I'll tell you about that. Right. So there is a special thing which can happen in heterogeneous catalysis, and that is what is called as shape selective catalysis. Okay, what is this? Right. So shape selective catalysis, again, I think from the name itself, you can tell what I'm going to speak. We are going to talk about catalysis reactions, which will happen only if the reactant molecules are in particular shape. Right. So the thing is, yeah, that's what is going to happen. So if and only if the reactant molecules are in particular shape, or I can even call it as orientation, right? If they are only in particular shape, or say if they are in a particular orientation, this catalysis will happen, right? And the glimpse of it, or say the basic foundation of it, we would have studied in your what is that? Chemical kinetics itself, collision theory again, right? So if you look back into collision theory, I told you that for the collision to be successful, there are going to be few factors, or say few criteria which has to be resolved, right? So what are they? I know that I should have enough amount of energy, some of the threshold energy, or say the activation energy must be possessed by the reactant molecules, right? And the second thing is that I told you that there should be proper orientation, right? There should be proper orientation for the collision to be successful. And I think I gave you an example also, NO reacting with O3, ozone, to form NO2 and O2, right? So hope you remember what and all we saw that time, how the orientation should be, right? So something similar to that, right? So this kind of things will happen in enzymes. Like if I go to my body metabolisms, inside my body also reactions happen, right? Right? So there, who acts as catalyst, right? I have my natural, my body built catalyst. These are what are called as enzymes, right? So these enzymes are what are called as metabolical catalysts. Like inside my body, they're going to catalyze thousands and thousands of reactions, right? And I know enzymes are highly effective, right? So even in micrograms, nanograms, like in very small amounts, right, they will be able to increase the reactions rate by 1,000 times, 10,000 times. They're very, very effective. These enzymes that inside the catalysts which are there inside our body, right, are going to be very effective. And obviously, we know it's called enzymes, right? So these, some of the enzymes, not all enzymes, but some of the enzymes give this shape selective catalysis. Okay, so how is it going to happen is it's like this. I think I've already spoken about it, but still we'll see again. Right. So again, what is that? The enzymes are again going to provide the surface for the reaction to happen. That's how it works. Like in most of the cases, you will just say that the catalysts are going to what to say, they're going to provide the surface for the reaction to happen. But it is here, it's not only about providing the surface, it's about the shape of the reactant molecule also. So we'll see how it goes, right? Right. So I'll see how enzymes are going to look, right? So I assume that this is my enzyme. Okay, this is my enzyme. Okay. So like I told you that enzymes are going to provide you the surface, right? So it's not like entire surface is provided, right? So this particular shape, whatever you're seeing here, this is what is called as your receptor site. Biology people, if you're there, if I'm telling something wrong, please bear with me, right? I don't like, but I think it should be correct. Am I correct? Do you have receptor? How many of you are from biology here? Is there anybody from biology? Not computer science?
So me.
Yes, sir.
So am I
Yes.
telling it correctly?
Yes,
Enzymes, receptor sites, all these
Yes,
are
sir.
right.
yes, sir.
Okay, fine. So receptor site is the site where the reaction is going to happen, right? Well, a receptor site is the site where the reaction is going to happen. Okay, now fine, I have the enzyme, I have the receptor site. Now what I have to do is I have to bring the reactant molecules and I have to make them react here. That's what I need to do. But the condition is that only and only if the reactant molecules are going to be in this shape, is it not? Only and only if they're in this shape. Obviously, it's not exactly same, but hope you understand what I'm trying to say. Only and only if these reactant molecules are in this shape, they'll be able to fit into this, right? And the reaction will happen, and then again it will go up, right? So hope you understand what I'm trying to say. Only if it is in this shape, say if it is in this shape or say this shape, whatever it is, now they will not be able to bind with the enzyme and then make the reaction happen. Only and only if the shape is like this, right? So then the reaction can happen. That is, they'll be able. This is my substrate. I'll call it. Right? Substrate means reactants. Right? So only if the substrate or the reactant is going to be in this shape, they'll be able to fit into this, and the reaction can happen. If not, no. So that's what happens in your shape selective catalysis. Now, this is not the only case where shape selective catalysis happens. Like if you're studied about hard water and soft water, have you studied? Can someone tell me what is hard water? What is hard water?
Which contains calcium, magnesium salts.
Correct. Right. So hard water is the one which have deposits of salts of magnesium and calcium, isn't it? So I know what are all the disadvantages if I use hard water, isn't it? Because if I'll not be able to use for washing, because they will not be able to produce proper froth or foam or whatever it is, right? So there are a lot of process involved in removing this calcium and magnesium salts. That is what is called as softening of water, converting hard water into soft water. That the process is what is called as softening of water. Softening is like this: SOFTNING. NING, right? So this the process called is softening, like converting hard water to soft water, right? So I know there are two types of hardness, right? So one is what is called as temporary hardness, and another one is what is called as what is that? Permanent hardness, right? So temporary hardness can be easily removed just by heating the water molecules, right? That now I think you already know, right? So when I go for permanent hardness, right? So in permanent hardness, I use something called as zeolites. Like basically there is you will be studying it more if I go for engineering. If at all you're going to take engineering, in the first year of your engineering, you'll be studying about the various process involved in softening of water, right? The applications point of view. But just now I'm telling that there are something called as zeolites, right? So the zeolites are the one which can help in softening of water, right? There are something called as ion exchange resins. Guys, you don't have to know these terms. I'm just giving you extra information, but zeolites are important, right? Okay, so there's something called as ion exchange resins, right? So in these ion exchange resins, I can just give you a, like say, a simple idea of how it works, right? Say I obviously know I'm going to have the M2 plus cations and some anions, say X minus. Right? Anion can be sulfate or say fluorides or whatever it is. So these are the hardness causing agents. Like M2 plus is my Mg2 plus or Ca2 plus, right? And the anion along with it. Again, it can be a mono negative or say more than one also it can be, but I'm just taking a generalized statement. Okay, so this will be there. Okay, what is going to happen is this both the water which is containing this is made to go through your zeolites, right? So zeolites, or say I don't want to go into the details. I'll just tell that I'm going to in the ion exchange resins, right? Say I have this RCOON, the sodium salt of any particular carboxylic acid. Okay, sodium salt of some particular carboxylic acid. It is exactly not like this, but just giving you an idea, right? So what is going to happen is if these two react, right? If these two react, my Na plus ion and the Mg2 plus ion will be replaced, right? Na plus ion and Mg2 plus ion will be replaced in the water. Basically, Na plus will go to the water, M2 plus will go along with the anion. Okay. Another thing what is going to happen is after this gets over, the anion is also getting replaced. Say, for example, I can have something like this RNH3 plus OH minus. It's another reason for removing the cation. Sorry, anion. Now, what is going to happen? The OH minus and the X minus would have gotten replaced, like say exchanged, right? So by this, I removed both the hardness causing agents. Okay, so this is how it happens. In the zeolites are the one which are there in the ion exchange resins. Okay, so why am I talking about zeolites in shape selective catalysis? Is that like the hard water has to go through different layers of softening. Okay, there will be different layers of softening. Okay, and after each layer, like if at all from one layer to another layer of the hard water has to go, right? So there will be small pores through which it will go, right? So again, the shape of this, or say the size of this matters. Okay, the size of the pores matters because like it's like something like filtration, right? So the size of the pores matters, right? So obviously it can come under shape selective catalysis, right? But zeolites here, I think you're not able. I think you're not convinced about what I said here, right? Because you don't know what exactly is happening. That's why I have to tell it in a very crude way, right? In a layman's language, I have to tell. But still, you just have to understand that zeolites are going to be shape selective catalysts, which are used in softening of water, as well as in your book, they would have given one special zeolite. And that special zeolite is what is my ZSM5. Okay, I'll tell you an experience, right? So when I was studying 12th, right? So this chapter was not my favorite, like was not one of the favorite chapters of chemistry, right? This surface chemistry. So what happened? I thought they'll not ask much questions and all that. I just went for the board exam with like not, I know all the basic things, but still not into the depth, right? So I went to the board exam and they asked me the question, what is ZSM5? I was like flipping. I read almost the entire book, but I never saw this ZSM5 because it's actually difficult to find. It will be at one corner of the book. They would have written ZSM5, which is state selective catalysis, which is actually used to convert ethanol to petrol. Or I would say, I'll not go into details. It's just used in petroleum industry. So this question came in 1 mark for me in my board exam, right? What is ZSM5? Where is it used, right? So ZSM5 is a safe selective catalyst which is used in petroleum industry, right? This was a one line which is given at some corner of this chapter and this was asked, right? So that's how NCERT works for you, for your information, right? So yes, so that's about shape selective catalysis. So this is also a zeolite here, right? This ZSM5 is also a zeolite. Which is used in petroleum industries. Okay, cool. I think that's it, guys. That is about catalyst here. What is the time? We still have time, so I can give you introduction. So yeah, that's about catalyst Did I miss anything here? No, nothing. So we have seen everything. So two parts of the chapter are over. That is adsorption and catalyst. Both are over. Okay. So the last part of this chapter talks about colloids. So we'll see what are they. So guys, any doubts? Shall we move on? Is there any doubt you want to ask me? So how can we use ZSM5 to produce more petrol without fossil fuels? No, that's what I'm telling. So if at all, you see, it is even beyond the scope of my knowledge how ZSM5 is used as a catalyst in petroleum industry, right? Yeah, obviously I require fossil fuels. If I don't have fossil fuels, maybe it's a special thing which can convert ethanol into something. I'm not sure. I think it's ethanol to petrol or something to petrol. I'll be able to convert it. Maybe crude oil to petrol, something like that. If at all you're really interested, please do research about it and tell me also. I'll also learn. Okay, fine. Right. So second part is also over. So now we are moving into right. Okay. So we'll go back. We'll take a flashback to your ninth class, second chapter is matter around us pure. Hope you remember the chapter name. Is matter around us pure? The answer is no, it's not. Right. So the thing is, if I say matter, right, I know what is matter. Matter is anything which has mass and occupies space, isn't it? So if I say any matter, this matter can be broadly classified into two types. And obviously there is one more way of classification, that is solids, liquids, and gases. That is different, right? This is another way of classification, right? So this way of classification, I'll be able to call matter as pure substances, and I have something called as mixtures, right? So what do you mean by pure substances? Pure substances are made up of one single type of entity. So this is made up of single entity, right? So this entity which I'm talking about, what is this entity? This entity can be of two types. It can either be atoms or it can be molecules, isn't it? So obviously, or you know what I'm speaking about here. So when it is atoms, when it is made up of only one type of atom, what is it called as? Elements, right? And if I say that it is made up of only one type of molecule, and obviously what I'm talking about here is my compounds, right? So obviously elements and compounds are the one which comes under pure substances, right? So elements are made up of the single entity called as atoms, and these compounds are made up of single entity called as molecules, right? So anyways, we know so much about them now. We know about the structure, so much we know about these, right? So we'll go there. We'll see what are these mixtures. So I would say mixtures are the one which is formed by mixing two or more pure substances, right? So if I have two or more pure substances, say I have water dissolved in NaCl dissolved in water. So NaCl is a pure substance, water is a pure substance. So when I mix them, but again, the proportion, how much I have to mix all these things doesn't matter, right? So you can ask me a question like this, sir, when I mix two or more elements, then compounds are formed. Then why am I not taking compounds under mixtures? Isn't it? Say for example, carbon plus oxygen will give me carbon dioxide, right? So carbon is a pure form. I mean, oxygen is also a pure substance. They are mixing together to form a compound. The only okay, I will ask you, what is the difference between mixtures and compounds? Did you understand my question? Right, I have carbon plus oxygen forming carbon dioxide or carbon monoxide. And here I have NaCl dissolved in water to form NaCl solution, that is the mixture. What is the difference here? In both of them, two or more pure substances are mixed to form something. That is one compound, that is another mixture. What is the difference here? What is the difference?
Sir, when we physically combine the particles, it is mixtures, and when we chemically combine, I think it is compounds.
Okay, fine, accepted. Any other difference? That chemically combining means what? Or physically combining means what? I would say it's not wrong, it's correct, but still more in depth going. What will you see?
Sir,
Hmm.
sir, in a compound, individual atoms or elements, they lose their property and they form completely new type of compound. But in a mixture, the individual entities, they don't lose their properties.
Understood. So basically, again, you're talking about physical and chemical changes, right? So assume like this, okay? So I really don't know what is happening, okay? I really don't know what is happening. So I ask you, like for all this, you are telling, no, I have to measure the properties before adding, after adding, and if at all they are different or same, accordingly, I'll be able to tell, okay, fine, this will be a physical change, this will be a, what is that? Chemical change, all that. But there is other way of doing it. I would say there's a little more easier way of doing it. Anything else? If I tell you, then you will see, yes, sir, correct. That will be the reaction. Compounds are going to follow all the laws of chemical combination. What is the first law? Law of constant proportion. That means if carbon and oxygen have to react to form carbon dioxide, their molecular ratio should be 1:2. If you don't put that, then the reaction means if you don't put that, the reaction will not be as like say as expected. But there is no restriction on the ratio or proportions. I can have any amount of salt, any amount of water getting mixed and forming a mixture. That is the main point of difference, right? So here the ratio doesn't matter. Here the ratio matters for me to form the compounds, and all the other points which you said are obviously correct, right? Obviously, there's going to be physical changes, chemical changes, properties will be lost, or properties will be retained. Depending on that, all these things, yes, there are the difference between compounds and mixtures. So the main, and as I said, one more difference would be the ratios. Here the ratios matters. Here the ratios doesn't matter. Anyways, so now moving on, I'll be able to further classify mixtures into two types, and we already know that. I have something called as homogeneous mixtures, and I have something called as heterogeneous mixtures, right? So under I know what is homogeneous mixtures, right? Throughout the solution, or I mean throughout the mixture, the concentration should be same, right? And the only thing which I have under this is my solutions. I call them as true solutions, right? So we already studied about solutions in depth in the solution stuff, right? So now when I go for heterogeneous, again I can have two types of them. One are what are called as suspensions, and the other one is what we are going to study, and that is my colloids, right? So colloids and suspensions are the examples of heterogeneous mixtures, right? So I know what a suspension, sand and water. There'll be a distinct layer which will be formed between the two components which are getting mixed, say oil and water. Again, as an example for a suspension, you will eventually see there is a layer which is formed between the oil and the water, right? So all these comes under suspensions, and colloids are the one which you're going to study. So colloids are heterogeneous mixtures, right? Fine. So what is the difference between a suspension colloid and a true solution, right? I would say colloids are in between your true solutions and your suspensions with respect to their particle size. Okay, so if you go to a scientist, right, if you go to a good chemistry guy and ask him, how will you define colloids? Okay, how will you define colloids? It's actually a very tough thing, right? Like it's colloids. There are so many types of colloids that I will not be able to give one general definition for what a colloid is, right? But again, I can give some general statements, right, regarding what is a colloid. So I told you the main difference between pure, there are so many differences, but the main difference between a true solution, suspension, and a colloid is that the particle size. Okay, fine. So how can I put it? Now, the first thing you can understand is that if it is going to be a true solution, right? If it is going to be a true solution, say I have a solution of salt in water, right? So I thoroughly mix it. So now if I will not be able to see the salt particles with my naked eyes, obviously I'll not be able to see. And one more thing is, even if I take a very strong microscope and look into it, then also I will not be able to look into the salt particles if it is a true solution, right? And obviously, in case of suspension, with my naked eyes itself, I'll be able to see what are the particles inside, right? If, for example, sand and water, I obviously will be able to see the sand with my naked eyes itself. But the colloids, I will not be able to see them with naked eyes. But if I use a microscope, right? Yes, there's the possibility that you will be able to see visualized colloid particles, right? So if I talk in terms of particle size, the maximum particle size is for your suspensions, and then your colloids, right? And then it is going to be your solutions. So solutions have the least of all sizes, and that's why even with the help of a microscope, you are not able to see the particles there. So I asked you, how will you define colloids? And this is how we are going to define colloids. Colloids are the one which are a heterogeneous mixtures, right? Which have their particle size from 1 nanometer to 100 nanometers, right? If you see that the particle size range is between in this, like 1 nanometer to 100 nanometer, and obviously it should be a heterogeneous mixture. If you see that, then it is what is called as a colloid. Okay, now just like how you had in true solutions, you had two components, that is your solute and solvent, right? Here also I have two components present, right? So it's very similar to solutions, right? So here also I have your two components which makes up colloids, right? So the two components are what are called as dispersed phase and dispersed medium, right? Dispersed phase and dispersed medium. Okay, so these two correspond to your solute and solvent, are very, very similar to your solute and solvent, right? So I would say this dispersed phase is what is my solute, and this dispersed medium is what is my solvent. But the only difference is that it is not going to be a homogeneous mixture, it is going to be an heterogeneous mixture. That's the way to put it, right? Okay, so depending on so many factors, I'll be able to go for classification of colloids. There's not going to be one classification. Say, I will say there are going to be so many. One of the classification is going to depend upon what is the phase of your dispersed medium and dispersed phase, right? And the other thing is going to depend upon how the colloids are formed. I have something called as associated colloids, macromolecular colloids, and all that. So based on how they are formed, they're classified, right? And the last part of classification talks about whether the solvent, that is the dispersed medium and dispersed phase, love each other, or whether they hate each other, will also be a criteria. That the dispersed phase and dispersed medium are going to love each other, or whether they're going to hate each other. Depending on that, also the type of colloid might change, right? And what else? And then you'll be studying about how to prepare a colloid. If you prepare a colloid, obviously the purity will not be much. So how to purify a colloid, and obviously what are all the other what are all the other properties of colloids, and eventually you will be able to see how to convert a colloid into a precipitate or a precipitate into a colloid. All these things you'll be able to find out. And I think I'll be able to complete this in the next class. Okay. So we'll see more about colloids in the next class, people. I think it's time for you to go, right? Fine then. Thank you. We'll meet again.
Thank you.
Thank you, sir.
Yeah, thank you.
இருக்கியாடா? ஹலோ, இருக்கியா இல்லையாடா?